Hey, what's up, guys? This is Cheng here. So today, LeetCode number 778, swim in rising water. Okay, so you're given like an n by n grade, right? So each element or each position represents the elevation of that point. And now the rainwater starts to fall. Now the rain starts to fall, and that's why the water will keep rising, right? So at time t, the depth of the water everywhere is t. Okay, and you can swim from a square to another neighbor for adjacent squares, if and only if the elevation of the waters, sorry, if both the elevation of the squares individually are at most t, right? And then you can swim in infinite distance in zero time, and of course you must stay within the boundaries of the grid. So our task is to find out the minimum time, right? So that we can swim from the top left corner to the bottom right corner, right? So yeah, so for example, we have a like 2 by 2 grid here, you know. So each of the cell has their own height, right? So the answer is 3 because so see at beginning the top left corner has like 0 height, which means we can swim here, but we cannot swim to any neighbors, right? Because we have 2, 0, 1, 3, right? So in order for us to swim from 0 to 2, we need to wait for 2 times, right? From 0 to 1, we need to wait for 1 times, right? And then either from 2 to 3 or from 1 to 3, we also need to wait some time, right? For example, from 2 to 3, we need to wait for another time. Here we need to wait for another 2 time. That's why the answer is 3, because we need at least 3 time to swim from the source, the start to the end, right? And yeah, so that's it, right? I mean the range is 50 by 50, right? So obviously this one is a kind of like a graph problem or like a search problem, right? Uh, so I was at the beginning, every time when we see this kind of so what is that? The least or the minimum values we're looking for in the graph problem. Uh, I actually at the beginning I was thinking about, can we use a BFS search, right? But the BFS search but seems like this graph problem is not like a BFS problem, because it has, like, as you guys can see, it has a weight, right? It has a weight on each edge. So from here to here, it's not free. We have to wait some time. So that's why this one is not like traditional BFS. And then we can definitely use Dijkstra, right, to solve this problem. And yeah, and we'll be doing the Dijkstra today. And there's also like another solution for this one. It's a binary search, right? Because binary search can also help us find either the least or the max values. And so for binary search, the key point for binary search is that we have to find the trend. Basically, there's like monotonic trend, right? While the value is either increasing or decreasing. So for this problem, basically when the time is increasing, right? So when the time is increasing along the way, right, there will be a time, right, we can reach from the start to the end, right? Because because we know by the time the water has the water is deep enough to cover all the square, then obviously we can swim. We can swim from one place, from the top left corner to the bottom right corner, right? So then we can simply search. do a binary search of the t here, right? A binary search the t here. So and we have hyperfunctions. Basically, given like a fixed t, there are some. Sorry, that's my Siri. So given like a fixed t here, we know in this grid we have some grids. Oh, sorry, we have some squares that are currently connected to each other, which means we can swim across them, right? And then we can just have a helper function with a given t, and can we swim from the top left corner to the bottom right corner, right? So that's that one. Actually, there's a third one. There's a third solution for this, which is the union find. Mm. So how does this union find works? Actually, it's a similar. I think it's a similar idea as the binary search. Basically, we have kind of a grid here. Let's say we have five by five. Okay. Maybe I should just write 4 by 4. Okay. Anyway, I'm almost done here. And basically, each cell has its own height, right? So what is the union find? How the union find can help us? Basically, if you know there's a algorithm called minimum spinning tree, right? So basically, here we're actually building like a minimum spinning tree to connect uh, the source and the target by connecting some of the path, by connecting some of the square, right? And we need to find the smallest time. So what is the smallest time, right? So the smallest time is the time that if we sort all this kind of element from smallest to the biggest, and if we process them one by one, right, from the smallest to the biggest, and by the time we process, let's say we have some, this is 0, let's say this is like 5 or something like that, right? And then right in the middle, let's say there's like this one, let's say the value is 7. So basically how this algorithm works is that we're using a union find, and then we sort each square by the height from the smallest to the biggest. And every time when we have like the current square, we try to do a union find with all its neighbors. Okay, and after that, we can check if the source and target has the same root. If that's the case, and then we know this value is the minimum time we're looking for, right? So this is like how the minimum spinning tree, right? Basically, by the time we have connected 0 and 5, then the the minimum spinning tree is completed. And since we are like processing from the smallest time here, then we are sure the current time, or this current value here is the minimum time we need to build this minimum spinning tree, right? Um, yeah, because yeah, I think that's the basic idea here, right? So, and of course, when we try to do a union with all the 4 neighbors, we simply cannot union all the 4 neighbors, because we have to have like a scene set here, where when we do the union find with all the neighbors, will only do the union with the square we have already seen before, right? I think it's obvious because let's say this one is 7, right? So since we're processing from the smallest to the biggest, let's say the neighbors has like 3, 4, and 6. This one is, let's say it's 10. Okay, so by the time we're processing this cell here, this square here, obviously these 3 neighbors, right, 3, 6, 4 have already been visited before, seen before. That's why we can do the union with them, right? But with 10, since 10 has not been seen before, we cannot do a union with here, because obviously, if we do a union with 10, it means that, okay, actually, because 10 has like a bigger value here. If union 10, if 10 has like uh, if 10 has like a connection with 5 here, right? It's with the end here, and then we're getting the wrong value here. It shouldn't be 7. It should be 10 instead, right? That's why obviously we only want to you know the the nature of the union find is like we only union with the value we have already a union before in this case, right? Yeah. So yeah, basically, if we were union a node that we have not been seen before, it means that the time will be increasing, right? Which will not be the 7 in this case. Cool. Yeah, I think that's all the explanation for all 3 I think solutions. I think we can start coding then, right? Um, so where should we start? Let me think. How about binary search? I think binary search is the most straightforward one. The binary search, right? So we have n going to be the length of grid, right? Then we have left equals to 0 and the right equals to n times 2, right? So the upper bound is this one because it says all the values is a permutation from n to n squared minus 1. That's why the right boundary is this one, right? And then the binary search, right? The template. So while this one is smaller than r, right? We have middle L plus L mod right minus left divided by 2, and then we're gonna have like a helper function. So I'm going to call it can reach. Okay, can reach from with the middle level water, right? If it can, okay. So now we're looking for the smallest, the minimum value, right? That's why we have to do r is gonna be the middle, and then the left else will be the uh, left will be middle plus 1, right? So this is a kind of template, because uh, so if you're looking for the minimum, we will be doing this middle equals to to the right, and the left equals to this one. If you're doing the maximum, right? If you're doing the maximum, and basically this is as if like this. You can try to picture this scenario here. If we're looking for the minimum, the maximum, and if this can reach, so this helper functions always return true, which means that not always return true. If this helper functions return true, it means that okay, the current value, works, right? So which it might be the answer. So for the minimum, for to look for the minimum values, let's say with the middle is right here, right? That's what it means that the middle could be the answer, right? And but since we're looking for the minimum one, right? So which means we need to look for this side, right? That's why we set this right into the middle, right? So similarly, if we're looking for the maximum, all right. So again, right? If for the maximum, if this one a helper function return true, it means that this one could be one of the values, right? But for this one, since we're looking for the maximum, that's why we need to look to the right side, right? Also including this one, right? That's why when we are looking for the maximum, when this thing happens, we have to do a left equals to middle, right? And then this one is going to be r dot middle minus 1, because for the maximum we're looking for the right side, right? So that's how you remember this template. And when you do a left equals to middle, you have to do this one plus one, right? I think I have already talked about that several times. Okay, so that's a little bit about the binary search, okay, template. And then what else? And then we just return the left in the end, right? So now let's implement that helper functions can reach, right? Reach of middle. So this helper functions here is simply like a DFS search, or like you can use stack or anything you prefer. Just trying to search from the beginning, from top left corner, and see if we can reach the end, right? With this current middle, basically with some constraints. So first, I'm going to have like this. Do a quick check. If this starting point is greater than the middle, right? Then we simply return false. It means that we'll never be able to move to anywhere from the top left corner. That's why we need to return false here. Otherwise, have a stack equals to this 0.0, right? And then we have a scene set, and then scene dot add, right? And then 0.0. And then directions. So this is all tedious coding here. And then do a while loop here, while stack current I, current j equals to stack.pop, right? So here I'm using a stack to do the DFS search. So if the CI equals to n minus 1, the CJ equals to n minus 1, then we return true, right? We know we find it. We find the path. It can reach basically. Or we do a search on 4 directions. Okay, so new I is going to be CI plus D0, right? And then new J equals to CJ plus D1. And then if this thing is in the range of n, same thing for the new J in the n and new I, new J not in scene, okay? And the grid, right? So the last one is it's a constraint we bring in with the middle, with the current level of the water, right? Basically, neighbor can only be visited if the water is higher than the height, than elevation of the square, right? Smaller than the middle. Okay. Then we do a stack dot append of new I new j, right? Oh, need another pair of parentheses here. And then scene dot add new I dot new j. Okay. And then in the end return false, right? Yeah, that's it. So let's run the code here. Okay, accepted. Nice. All right, cool. So it works. Yeah, so that's a binary search, right? I mean, the time complexity. So obviously here we have the range is like this. So we have a log n square, right? So that's the binary search. And for the helper functions here, it's just while loop. So the worst case scenarios, we have to search the entire graph, right? That's why we have a n square log n square, right? So that's the binary search time complexity. And so next, let me think. Yeah, Dijkstra, right? So let's do Dijkstra next. I think we have already basically analyzed a bit about Dijkstra. Basically, the reason we can use Dijkstra is because from one node to another, so from one square to another, there's a cost. In this case, it's a time we have to wait, right? In case this one is it's lower than this one, right? I mean, this is 10. Let's say this is 5. If we want to travel, you want to swim from this one to here, we have to wait for 5 times, right? But if this one is 10, 10, 5, then this one is 0, right? Then it's free. Okay, cool. So now we have a graph with the with a weighted edge, right? And we want to find the minimum cost from top left corner to the bottom right corner, right? So that's a perfect candidate for the Dijkstra. Okay, cool. So for Dijkstra, let me think. We need distance, right? I mean, I think it's not distance. It's like I'll call it cost, right? So we need a basically two-dimensional array to help us to store the minimum cost, right, from between any two nodes here. Okay, and at the beginning we have a cost at 0, 0, right? So what is this one? So the cost. So keep in mind this one is not 0. It's a what? It's a grid of 0, 0, right? Remember? So the first one does not necessary to be 0 all every time. If the 0, 0, let's say if there's 10 here, 10 2 5 and 1, right? So for example, this one here. So what is the answer for this? It's 10, right? Because we're standing at the top left corners, but we cannot move anywhere until the time 10 is equal to 10, right? And by the time it is equal to 10, we can simply move to anywhere, right? Including this one. That's why the cost 0, 0 is the value of the grid 0, 0. Okay, and then the product queue, right? For the Dijkstra, and we have the grid of 0, dot 0, and then the coordinates, right, along with it. Then we also need a scene set, right? And then the while product queue thing, right? Then the cost dot ci current I current j heap pop product queue, right? And then we do a scene dot add ci dot cj, right? So we only add to the scene after we pop out from the product queue, because there could be multiple entry items for the same coordinate in this product queue, and we only add it whenever it's his turn to be processed, which means this one has the smallest cost, right, for the Dijkstra. And then for D, and we need to define this. But luckily, we can copy and paste. We don't have to type in this. And I guess we also need this N here. Okay. So for D, actually, I'm going to copy this part, because they're pretty much the same. So we have a D here, and this part is that, and this is not this one, and we're going to remove this part, right? So now here inside, so part of the Dijkstra problem, the template, we have a new cost. The new cost will be the grid from the new place, new I minus new this new one, subtract the grid of this one dot cj, right? So it seems like this one, but this one is not correct. First, this one could be smaller than this one, right? So the new cost could be negative. That's why first thing we need to add is the maximum between 0, right? So in this case, we're sure that we'll always get a 0 for negative values. And there's a second issue here, because for example, right? So I have already given you the example here. So let's say we have 10, we have 1, and then let's say we have 5, 2 and 5. Okay. So for example, in this case, right? If you're only trying to do the new cost with this formula, okay, so at the beginning we have 10, the cost is 10, right? So from 10 to 1, this is 0, right? And we're fine. But from 1 to 5, we have 5 here, or we have 4, right? So are we saying that, from here to here, if we follow this one, the cost from here to here will be 14 instead of 10, because the real answer is 10 instead of 14. That's why we cannot simply just do this one with the previous one. Instead, we should also do a comparison with this one for this one with the current of the cost. And we're getting the maximum between two of them, and that's how we can get the correct, basically the previous cost, right? All right, cool. So now we have a new cost, and then we can do the diagonal part, right? And then if this thing is smaller than the cost of new I and new j, right? And then we update. And we do a heap push, right? Priority queue dot we have a new cost plus cost, and then new I, new j, okay? And then don't forget to update this cost, new I, new j equals to this, right? So that's it, and that's the whole dextro. And then in the end, just return the distance of -1 and -1, right? So that's the value, right? That's the answer we're looking for from the starting point to this last one. Cool. So run the code. Heap heap pop. Excuse me. Oh, sorry. Yeah, I was using distance at the beginning, then I changed it. That's why I mistyped that. Okay, accept it, and then cool. So this one Dexter also works, right? And for the time complexity for the Dexter, and I think it's V plus E log V, right? So that's that's time complexity for Dexter. And as when we convert it into this problem, so the vertices and edges, right? So we have vertices. Vertices are like n squared, right? Plus, how about edges? Edges is also n squared. Okay, and then we have a log of n squared. Right, so this one is gone, right? Actually, as you guys can see, this one is the same as the binary search, the time complexity. Okay, so that's the dextro for you guys. And the last one, what is that? Oh, the union find, right? So let's do the union find with the minimum spinning tree, which is also called Kruskal algorithm, right? If I'm not mistaken. Okay, so the last one is the union find. For the union find, so to do the union find, we have to create the parents, right? So the parents list first. So because at the beginning, everything is its own parents. So it's going to be the range of n squared, right? And then for the union find, let's define the union find function here. So the first one is find if x not equal to the parents of x, right? So we do a parents dot x equals to the find of parents of x, okay? And then we return the parents of x. That's the find, and then the union, right? So this one is like a find with the path compression. I have already talked about this part a lot of times, many times. So I'm not going to repeat that here today. So for the union, we have R1 is going to be the find of x, right? And R2 is the find of y, okay? And if R1 is not equal to R2, we do a parent of R2 equals to the R1. So again, here I'm skipping that the the rating part, right? So because actually to make this find and union a real O1 time complexity, ideally here when we do the unions, we should also compare the weight for each of the spinning tree, right? And we'll only append sorry, not the spinning tree, the tree for each of the root group. So we'll only be appending, assigning the root who has the smaller weight to the root who has a larger weight. That's the way we can make this like a tree structure balanced, right? But here I'm just simplify that union version a little bit. Okay. Yeah, basically every time if you really want to do that, basically we have a like I think there's a score something at the beginning. We have everything. It's gonna be 0, right? And then this is n this one. I think that's how we do it, right? So basically, if this one doesn't equal this, basically if the score of R1 is greater than the scores of R2, right? And then we do this. We do a parent of this one, okay? Else, right? Oh, and when we do this, we also need to update the scores of R1, right? So this scores of R1 gonna be the increase, gonna be the sum of this, right? Else we do it in a reverse way, right? So now we're assigning the parents of R1 to R2, and now the score of R2 will be increased by this, right? Something like this. Yeah. Okay, cool. So that's the union find template, right? Pretty straightforward. Now the next thing is that we have to do this minimum spinning tree, which means we have to sort the coordinates by its value from the smallest to the biggest. So I'm going to call it sorted position, right? And then here I'm going to write a pretty long like expression here. So we need to have a sorted. So the first part is a list. So it's a list of the coordinates. So it's going to be the I and j, right? So where does ij coming from, right? So it's going to be for I in range n, and then for j, oh, where did I go here? For j in range n, right? So that's the list we're trying to sort. How about the key to sort? And then we need this kind of lambda function, right? It's going to be x, and the value we're looking for is the grade of this x, right? So the x is a tuple here, so, and the first one is the I, and the second one is the j, right? That's how we do the sorting. And then yeah, I'm going to copy this. I think we also need these two variables here. Now we can do I think also the scene stats. I think. So now we start processing trying to do the union from the smallest square, the lowest square, right? For I and j in sorted position, right? So every time we do this, we add this one to the scene set, right? So to mark it, we have okay. So this position has already been visited, which means we can union with it later on. Okay, and then I'm also going to copy this part. So there's always something that never change, you know. For example, this part. uh, oh yeah, I think this is exactly what we need. So right, because we also this part now this is gonna be instead of not, right? Because we should only union with the previously visited node. Then union Yeah, so for the union, whenever we have a 2D board here, we have to, since I like you guys as you guys seen here, right? So basically we flattened this 2D grid into a 1D list here. Okay, and then to find that location in this 1D list, we can simply convert this one into do this conversion plus j, right? And then new I times n plus new j. That's basically the index for these two coordinates. Okay, cool. Then after this union, after union this one, do the union for this one, we can simply check if the find 0, right, is equal to the find of n minus 1. Okay, if this is true, it means that, okay, we have find a path, right? Or we have finished building the minimum spinning tree to connect the source and target. And that's when we can simply return a grade of I and j, right? Cool. I think that's it, right? If I run the code, did I? Oh, yeah. Before. Oh, oh, I see. Yeah. Let me move this one down below. Okay. CI. Oh, I see. So this part, yeah, that's a price you need to pay for copy and copy and paste, right? And I hope this one this time is correct. What? Uh, scores. Oh, I think this part is it. Yeah. All right, accept it and then submit. Cool. So it also works, right? And yeah, I think that's it for the union find, right? And the time complexity for the union find, right? And like I said, the find and union with this path compression for find and with the score or the weight with union, so we can treat this both two with the operation with O1 time complexity. Okay, and that's why so the real time complexity falls into this part, right? Because here, here we have this is n square, right? We have n square of the position, right? And then here's the constant for loop here, and then here's O1, right? This is also O1. So basically, this for loop is n square. So, but the real deciding factor is this sorting part, right? So because we have how many elements we have here, n square, right? Right, and the sorted is n square log n square, right? See, it's exactly the same as the previous two solutions for the union find. And yeah, I think that's everything I can talk for this problem. I'll just stop. Okay, cool. Thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.